Today, we're going to unravel a really interesting puzzle in computer science. It's all about quicksort, an algorithm that pretty much every programmer learns, but one that comes with a pretty serious warning label.
You know, on paper, quicksort has this dark side. Its performance can completely fall off a cliff. We're talking about it grinding to a halt in a way that should make any engineer really nervous about using it for anything important.
And yet, despite that huge risk, it's everywhere. It is the go-to sorting algorithm in so many programming languages and libraries. So what gives? Why are engineers all over the world betting on an algorithm that can fail so spectacularly? Well, that's exactly what we're going to figure out.
Okay, let's get into it. To really understand why quicksort is so popular, we have to start with its core idea, which is actually beautiful in its simplicity. It's all about divide and conquer, but with a special twist.
So here's the game plan. First, you just pick any element from your list, that's your pivot. Then, you just shuffle everything around so that all the items smaller than the pivot are on its left and everything bigger is on its right. That's called partitioning. And then, you just do that exact same thing again and again on the two smaller chunks until the whole thing is sorted. Simple, right?
And this is where the magic happens. Unlike other algorithms you might know, like merge sort, there's no complicated step at the end where you have to merge everything back together. Nope, the sorting happens right there inside the original array. We call that in place. And that is a massive clue to why it's so fast in the real world.
But that elegance, it hides a pretty big vulnerability. Because everything, and I mean everything, depends on the choice of that one little element, the pivot. It's the algorithm's greatest strength, and, at the same time, its Achilles heel.
Yeah, the pivot you pick makes all the difference. If you get a good one, something near the middle of the values, you get these perfectly balanced partitions. The problem gets chopped in half every single time, which is super efficient. But pick a bad pivot, say the smallest or the largest item in the list, and your partitions become completely lopsided. You're barely dividing the problem at all, and the whole thing just collapses.
This makes quicksort what we call data sensitive. Its speed isn't consistent. It can change like crazy based on the data you feed it. For instance, if your data is already sorted and you just naively pick the first element as the pivot every time, well, congratulations, you've just triggered the absolute worst-case scenario. So this brings us to the numbers, right? The theoretical performance, the big O notation that we use to talk about algorithms. And honestly, looking at these numbers just makes the whole thing even more mysterious.
In its best and average cases, quicksort is amazing. It runs an O of n log n time. That's the gold standard for this kind of sorting. But then, you see it. That worst case, O of n squared. That isn't just slow, that's a catastrophe. For a big data set, n squared is the difference between waiting a few seconds versus waiting hours or maybe even days. That's the risk that freaks people out.
But here is the absolute key to the whole thing. That terrifying worst-case scenario, it's practically a ghost. With even the simplest strategies for picking a decent pivot, the chances of you actually hitting that worst case with random data become, well, astronomically low. The average case is what we see almost every single time.
And that brings us to the real answer. The reason quicksort is king isn't just that its average case is good. It's because its average case is unbelievably fast on actual physical computer hardware. This is where theory gets a reality check from engineering.
So, why do modern CPUs just love quicksort? Well, first, it sorts in place, remember? So it's not wasting time asking for more memory. It also has what we call excellent cache locality. That's a fancy way of saying the data it needs next is usually already nearby in memory, so the CPU can grab it super fast. Throw in fewer data swaps and really simple code loops, and you've got an algorithm that is just built for pure practical speed.
And this really points to a deep truth in software engineering. The theory, the big O notation, it's a super important guide, but it does not tell the whole story. It doesn't really account for things like memory caches or how a processor is built. And in the real world, those things matter a lot.
This all becomes crystal clear when you put quicksort head-to-head with its main rival, merge sort. Merge sort is the safe bet. Its worst case is a guaranteed O of n log n, no matter what. But it pays for that safety. It needs extra memory, and its cache behavior is just okay. So the trade-off is right there. You use merge sort for systems that demand predictability. You use quicksort for systems where raw average speed is what you care about most.
So you might be thinking, okay, but what if you could get the speed of quicksort without the risk? Well, that's exactly what modern computer science has done.
We didn't just accept the risk, we engineered our way around it.
Modern versions of Quicksort have a whole bag of tricks to dodge that worst case. Instead of a predictable pivot, maybe they pick one at random, or they look at 3 elements and pick the middle one. For really tiny subarrays, they switch to a different, simpler sorting algorithm that's actually faster for small lists. Some even have a built-in panic button called intro sort. If the recursion gets too deep, a sign you're heading for trouble, it just switches to a different, totally safe algorithm to finish the job. It's the best of both worlds.
So the bottom line is this: the quicksort that's running on our machines today is not the simple, naive version you learn about in class. It's a highly optimized, battle-tested piece of engineering designed from the ground up for both speed and safety.
This really boils the whole debate down to its essence. When you absolutely cannot afford a performance surprise, when you need a guarantee, you choose merge sort. But when what you need is the fastest possible performance on average, you choose the engineered version of Quicksort.
And that's the real lesson here, isn't it? It's not about just knowing which algorithm is the best. It's about understanding the trade-offs, understanding the context, and seeing the difference between what's perfect in theory and what's practical in reality. That is the heart of engineering judgment.
So I'll leave you with this question to think about. Where else in technology or even in our lives do we pick the option that's faster on average, even with a tiny bit of risk, over the one that's perfectly safe but always a bit slower? That line between the optimal solution and the practical one, that's where all the interesting stuff happens. Thanks for joining me.